In this second video, we're going to talk about natural gas markets. Okay, so natural gas, it's one of the most important energy markets. It has been gaining share relative to other fossil fuels in the recent past, particularly for electricity generation. And this is actually a good thing for the environment because even though natural gas is still a fossil fuel, so it still releases CO2 and other pollutants, it's much better than the alternative, which has been coal. Okay. All right, units. Natural gas, it's usually traded in units of energy. We have covered the joule, which is the main unit, and then we also covered this alternative unit, the kilowatt hour or the megawatt hour. So natural gas, particularly in Europe, is traded in units of kilowatt hours or megawatt hours. But in other markets like the US or the UK, it is traded in a different unit, the British thermal unit, right? So you have the definition here of what it means. For our purposes, it's important to note it is just one more unit of energy, and it is related to our benchmark unit, the joule, through this equation, so this relation. What we will do is we will always convert from one unit to the other by going back to this common base, which will be the joule. Okay. So there is a thing here which is important to keep in mind, which is a bit weird, but it's just the way things are defined, so we just have to memorize this definition and that's it. So and it's this warning that you see here. In SI units, the M, when you see an M in front of a unit like the watt hour or the joule, it means 10 to the 6, 1 million. So the M is 1 million. But M in front of this new unit, this BTU, stands for 1000, right? So if you see two M's, like MMBTU, it actually means 1 million. So two M's in front of BTU mean the same as one single M in front of a SI unit. All right. There's some information here about market participants. Please skim through this. Production as well. Read this part here. There is an interesting note here about shale gas, which has been an important development in the recent years. It's a new technique to extract natural gas, which has led to a lot of new production, which in turn has changed the market dynamics. The price of natural gas has become lower than it was some years ago. This has been going on mostly in the United States. You can see here that the shale fraction of gas has increased a lot. They have actually switched from being importers to becoming exporters. Transportation and storage. Again, you can read through this. Natural gas is transported through pipelines, and there is something important here that we need to keep in mind, which is the following. So this is a map of the US. You see all the pipelines that exist there. You can look up similar maps for other countries, for Europe, and so on. But taking the example of the US, there will be one point here which becomes very important, which is this Henry Hub. The Henry Hub, let's see if I can make this bigger. The Henry Hub is one particular point in this big network of pipelines. In the United States, it's located right here, in this point here. And this becomes the reference for the whole market. So the price in this particular location is the main price for this whole market. It's the reference price. Okay? So it's a good analogy. It's more or less like you have an index for the stock market, which is the number you use to describe the whole market. This Henry Hub price, it's the price at one specific location, which is used to describe the whole market. So you have that reference price, the Henry Hub price, which may be a number like this. And then you typically describe the prices in other locations as a spread between that hub and whatever location you're talking about. So this Waha hub is some other hub somewhere out there. So you have the difference between the Henry hub and that whatever that other hub is. Well, Waha hub is actually here, right? Liquefied natural gas, can read through this. It's actually, again, an interesting recent development that, I'm sorry, not the technology itself, but the use of it. So the US, which used to have large facilities in its coast to import natural gas, now, given all the shale production that they have actually converted those facilities to, instead of importing, exporting natural gas. And again, that has influenced the global price dynamics of natural gas. Storage. This is important for the behavior of prices. So you can read through this part here. The main point to take away from this is that storing natural gas, it's complicated because it's a gas, so you need kind of a sophisticated facility to store a gas. It is possible, so you have all these alternatives here that people use, but it's something that you cannot do for very large amounts for very long periods. So you can store it for some time, some quantity, but not that much. And that will influence the way spot prices are related to future prices, as we'll see later on in these notes. Uses of natural gas. It has these uses that you see here. You can read through this. One interesting application is to use natural gas to generate electricity. So this example goes through that. It's similar to that example we did in the previous video, where we used diesel to generate electricity. So the difference here is that instead of using that fuel, now we are going to use natural gas. Okay. So a power plant does, a combined cycle gas turbine does that with an efficiency of 55%. Recall again, this number means that for each unit of energy that goes in, only 55% of energy comes out, in this case in the form of electricity. And this is the price of natural gas, dollars per million BTUs. And again, the question is, how much does it cost to generate 1 megawatt hour of electricity? Right? There is a note here to help you convert from the units of natural gas, million BTUs, to the units of electricity. This is the answer. If you may want to pause the video now and try to do this on your own, and I'm going to show you the solution in a second. So this is the solution. I'm going to post this image in Moodle as well. That first conversion that we wanted to do from megawatt hours to million BTUs is done here. Again, so these are all the steps you need to do, taking into consideration that, again, this M in front of joules is the same as 2 M's in front of BTUs, right? And then the cost of 1 megawatt hour is the inverse of the efficiency, as we have done before, and then converting this is the total amount of energy that I need to input, convert that from electricity to BTU, sorry, from the units of electricity, megawatt hours, to the units of gas, which are million BTUs, by using this factor that we just got from here, and then multiplying by the price of 1 unit of gas. And that gives you a number of 2171, right? So what this is saying is that a gas power plant will be able to sell electricity in the market at a value of 2171 per megawatt hour. These numbers are kind of in the right ballpark. If you recall from last video, we talked about the diesel generator. This was actually a peaker plant, which would only generate in periods of very high demand, and the price there was extremely high. I forget exactly how much it was. It was around $200 something per megawatt hour. Here it's a number much lower, in the order of 20, which is much more in line with the prices you see on the market. So actually, if we go to the market right now, let me open the market webpage. You can see here. This is that same market we talked about in the first class, the PJM market in the US. You can see the price there. Today it's 7.4. Right? Today is Sunday early morning in the US, so it's really a very low demand point. You can see here, it's people are still asleep, so the demand is still low, the price is still relatively low. But usually these prices are in the range of 15, 20, something around that. So as we'll come back more to this market as we talk about electricity markets in the future. But what you want to keep in mind now is that these type of power plants that we are describing here are the ones that typically set the price in that market. All right. Another concept here, people sometimes talk about this thing called the heat rate, and this is just a complicated way of talking about the efficiency of a given power plant. Well, it's complicated, but it will make our calculations easier later on. So the heat rate is defined as this, the fuel used by the power produced. So two things here. If this was upside down, it would be just the efficiency. It was the output, and this is the input. So if I invert this ratio, it would be the usual efficiency. So this is the efficiency. The heat rate is the efficiency inverted. What I have here is the input. What I have here is the output. Plus, it has some other change. Namely, instead of using the same units, what I'm using here are the units of gas, and here the units of electricity. So this is like the inverse of the efficiency, but with messed up units, if you will, right? So here, this table shows you how to convert from the efficiency of a given plant to this heat rate. Why do we do this? Well, because once we have this number, once we have this heat rate, which corresponds again to the efficiency, but through this transformation, then it becomes easier to do these types of calculations that we see here. So the spark spread is very similar to the previous spread we talked about, which was the crack spread for the oil refinery. So now this is spark, because the name here, the spark, is the idea is that when you burn gas, you need a spark to start to burn the gas, and that's where the name comes from. The crack spread was the spread you get from cracking the oil molecule, from splitting the oil molecule. So the spark spread is similarly the difference between the output value and the input value. So what you see here is the price of 1 unit of electricity that comes out. And what you see here, turn off something here that is, I should have turned off before. Okay. What you see here is the price of the input that you need to generate 1 unit of the output, right? And that's the advantage of using the heat rate. The heat rate immediately gives me how much input I need to generate 1 unit of input. So this is a quantity of energy that I need, and then I just need to multiply that by the price of 1 unit of the input, right? So this is an example that is almost trivial. You just need to plug in these numbers in this formula and compute the spark spread for these numbers. I'm going to post the solutions as well in the same picture of the previous example. Trading natural gas. There are a bunch of trades that can be done. Read through this. We will be doing applications of this when we get to futures. Okay? And finally, there's an interesting comparison here between spot and forward markets. The point was, as we described before, natural gas is hard and expensive to store. So the relation between spot prices and future prices becomes different from what you typically see in other financial markets like the stock market. Right, so the relation, there is some relation, but it's not as tight as in the stock market, for example. So this table here describes these differences between forward and spot prices. Please read through this. Then at the end, I have some exercises with solutions at the end. Please go through this. Okay.